Hello all. Let's start our lesson today. We will continue from what we had last Thursday. We did the first two steps of this hypothesis testing. Let's review a little bit. That first, the first step to claim is a statement that has exactly one truth value. And in this chapter, we will deal with claims with one parameter, either population mean with sigma known. Oh, by the way, this is not in our textbook. This is not in our textbook. And then population mean with sigma unknown, population proportion P, and population variance or population standard deviation. Then once we get the claim from that claim, then we go to step 2, we develop the hypothesis. We have, for each claim that we have, we can develop two competing complementary hypotheses, null hypothesis and alternate hypothesis. Now, the null hypothesis contains equal sign, and the challenging hypothesis does not have equal sign. Okay, now in the notes that the claim may become the null hypothesis, may becomes alternate hypothesis, depending on does it contain equality or not. Okay. The claim becomes alternate hypothesis if the claim does not imply the parameter contains equality. Okay, but if it implies that it contains equality, then it becomes null hypothesis. We will always write our hypothesis in braces, H0, H1, and then parameter with this sign in the middle and then constant. Now that's for the null hypothesis and alternate hypothesis. And last Thursday we did step 1 and 2 for question A, B, and C. Let me shorten this. This is done last time. Anymore. Likewise here, we did it, and I hope you actually reviewed that though. We did this one also. I believe we did question 1 as well. Now let's do question 2 and question 3, at least for review. The National Center for Health Statistics reports that the systolic blood pressure for males 35 to 44 years of age has mean 128. Now, in a study of business executive, the random sample size of 100 executives, that's the N is 100, has the mean systolic blood pressure to be 134. Do the data suggest that the mean systolic pressure for business executives is higher than 128? Now remember, we just need step 1 and 2, so I only provide you what you need to do step 1 and 2 here. There are some missing information. For example, do we have population or sample standard deviation? Okay, and how about the significance level? Now, by the way, if the significance level is not given, then we will use 5%. Okay, but that's later. Let's do step 1 and step 2 for now. Step 1, the claim. Notice that the claim was not explicitly given to us here. So I need to rephrase from the context. Do the data suggest that? I think I will take that as my claim. The mean systolic blood pressure for business executive is higher than 128. The mean systolic blood pressure for business executive is higher than 128. And then step 2, hypothesis. Braces, null hypothesis, alternate hypothesis. Oops. Higher than 128. So the mean is higher than 128 because it doesn't have equal sign. Then it goes to the alternate hypothesis. So the claim is here. Okay, so the null hypothesis will have the complementary of that statement. Now again, let me emphasize that our textbook will just say null hypothesis mu equals to 128. Okay, and if you do so, it's fine. If you write the green one for the null hypothesis, then it's fine. Okay, but you still need to get it has to be in this form though. The only change will be here if you follow the textbook. Okay, if you follow the textbook. Now, that's for question 2. Now, let's see question 3. An analytical chemistry lab is conducting quality control tests on a drug. A single dosage of the drug should contain 8 milligrams of active ingredient. Now, of course, there will be a small amount of variability due to imperfections in the production process. But the mean of all dosages produced must be 8 milligrams. Now, in 20 random dosages, so that's our N, the mean amount active ingredients is 7.7. Do the data suggest that the mean amount of active ingredient in all dosages produced is different from 8 milligrams? So step 1, the claim. We don't have the claim given to us explicitly, but from the question, we rephrase it that this will be the claim. This will be the claim. Okay, the mean amount of active ingredient in all dosages produced is different from 8 milligrams. In step 2, hypothesis. Null hypothesis, alternate hypothesis. The mean is different from 8 milligrams. So that goes to the alternate hypothesis again. But again, it's not always. It's not always that the claim goes to the alternate hypothesis, not all the time. It depends on does it have equal sign or not. Okay, keep that in mind, please. Now, of course, then the null hypothesis will be the complement of the alternate hypothesis. Now, we go back to procedure. We have done step 1, which is the claim, and step 2, hypothesis. Step 3, now test statistic. The test statistic depends on what we are testing. Okay, if we are testing population mean with sigma known, then the test statistic will be this guy here. I think it's not really that clear, huh? Let me rewrite it there. It's not clear. Let me rewrite it. And it will be Z equals to sample mean minus mu over the standard error. Okay, that's the C score. That's the C score. That's the C score. Now, the mu here, let me use this one. The mu here always come from, always comes from the constant in H0. Okay, always come from the constant in H0. So that's the reason you see that in our textbook and other textbook, especially recent one, that their null hypothesis always being expressed as parameter equals to constant. They always use equal sign. Okay, so my point of view is null hypothesis, alternate hypothesis supposed to be complementary to each other. That's my point of view. Okay, but textbook point of view, just like before, just like what I said before, that their point of view, they use equal sign because of this. That's the number they will use there. Okay, now, but in other case, suppose we don't know the population standard deviation. We don't know population standard deviation, so we will use sample standard deviation instead. Then, just like confidence interval case, we don't use T. We will use Z. We will not use Z. We will use T. But the formula is the same: x bar minus mu over S over square root of n. Okay. Now, in case you wonder where we get these formulas from, well, that's the foundational formula. But remember the margin of error thing, right? Margin of error equals to the critical value times, let me use C instead. C times sigma over square root of n, right? Now this E here, this margin of error here refers to the x bar minus mu. So the C score will be x bar minus mu over the standard error. Okay, that's how we get that formula. Of course, then what happens if we don't have the sigma Thomas? Then you change this to S, but then you change this to T. But then eventually you get that formula anyway here. Okay, now that's for the if we have the population standard deviation or not. Now, later on, I think after the break, then we will work on population proportion, just like in confidence interval case, when we did critical value from population proportion, we use C-score. Now here, then the C-score will be P hat minus P over square root of P times Q over N. While the chi-squared, if we are testing population variance or population standard deviation, chi-squared will be n minus 1, that's the degree of freedom, times samples variance over the claim population variance. Okay, now so even though the formula look different, but all of them, the distributions of test statistics here corresponds to the distribution of for critical values we use in confidence interval. So you need to memorize the one for confidence interval first. Memorize the critical value for confidence interval. Okay, start with that one and then we go on. And then what else? The parameters used in those formula comes from the constant we have in null hypothesis of step 2. Okay, now in our next examples, there will be 3 examples. We will apply steps 1, 2, 3 on hypothesis testing for population mean with sigma known. Okay, for the next examples, we will just apply that to the first case. And then we go on to the step 4, step 5, and step 6. Okay, let's start. Question 1. A principal in a school, but we will still do step 1, 2, 3. Okay, so we will still do step 1, 2, 3. A principal at a school claims that the average IQ of students in his school is above 100. So that's the principal's claim. A random sample of 40 students, so n equals to 40, IQ scores is found to have an average of, so x bar is 112.5. Suppose overall IQ score has standard deviations of 15. So not from that sample, but the overall. So that's what's given to us. Okay, so step 1, the claim. The average IQ score, IQ of students in the principal's school is above 100. That's the claim. Step 2, hypothesis. The average is above 100, so mu is greater than 100. Now, of course, simply because your mean is greater than 100, doesn't mean the overall population of all students in that school has the mean above 100. No, no, we cannot conclude that way, but we need to do some hypothesis testing. Okay, then step 3, oh, where's the claim? The claim is here, huh? This is the claim. That's the claim. And then test statistic. Test statistic, little note, the testing mu with sigma known. Then we will use Z. Okay, so the test statistic Z equals to X bar minus mu over sigma over square root of n. The X bar is 112.5 minus the mu is 100. The sigma is 15 over square root of 40. Now then you use your calculator. I get 5.27 something. That's our question one. Let me highlight that differently so that we can see the partition. Okay, now that's for question one. Let's go to question two. Suppose we do question two. Suppose we want to test whether or not girls on average score higher than 600 on SAT verbal section. So we want to test whether or not girls on average score higher than 600 on SAT verbal section. I think that would be the claim. Now we also happen to know that the standard deviation for girls SAT verbal section is 100. Okay, so the sigma is 100. A random sample of 20 girls gives us a sample mean of 641. Okay, now the thing is the sample size is less than 20. The sample size is less than 20, and for that reason, the question supposed to say later on that the population, basically the overall SAT score, verbal section score for girls is known to be normally distributed or approximately normally distributed. Then we can use the following model. Okay, for now we just assume that we can use this model. The claim will be girls on average score higher than 600 on SAT verbal section. Second hypothesis, the null hypothesis, alternate hypothesis, the mu is greater than 600. That's the claim. Now, it happens that the claim is with the alternate hypothesis again. Actually, that's quite common. It is quite common that the claim will go to the alternate hypothesis, but the key is not with that the claim goes to the alternate hypothesis. The key is does the claim includes equality or not? Okay, do we have equal sign included in that claim or not? If it doesn't, then it goes to the alternate hypothesis. If it does, it goes to the null hypothesis. Okay, and then step 3, oops, step 3, our test statistic. Test statistic. And C equals to, again, we know the sigma, right? So, and we are testing the mu. So we use C. This is x bar minus mu over sigma over square root of n. You can just plug in numbers right away, but I assume you don't memorize that formula yet. So I write it down, write the formula down first. Okay, 641 is the sample mean minus the claim from the null hypothesis constant, that's 600 over 100 square root of 20. Now, I need to make sure that you know how to punch this into your calculator. I need to make sure you know how to punch this into your calculator. Okay, let's make sure you get it. New share, going here. Okay, now the thing is, the numerator should be in groups. This is one group, this is another group. Okay, so make sure you use parentheses. Make sure you use parentheses. Make sure you use parentheses when you apply to the calculator. So parentheses, the difference of 641 and 600, then divided by the quotient of 100 divided by square root of 20. So make sure you use that double parentheses. Okay, make sure you use that double parentheses, and then 1.83358. 1.83358. Is that the number I have? Okay. Now that's the test statistic. Yeah, earlier I forgot to mention to you how to use your calculator. Now I hope you already know how to do that. Okay, now let me go on with example 3. I know some of you may say, Thomas, it's so boring. That's basically the same thing again and again and again. It is true. It is true. Okay, but I want to make sure you're really good here. Okay, because for other cases, basically using this as a template. Now, at that time, when you say, Thomas, I don't know how to do that. Well, basically, you don't get bored enough yet here, right? Okay, you need to get bored here. You need to get bored here. Okay, now test whether the population mean from which a random sample of size 16 taken. Oh, that's the end then. Significantly less than 10 if the population from which the sample was taken is normally distributed with assumed mean 8.4 and variance 10.24. So the mean is 8.4, the variance is 10.24. Okay, now this is the population. That's the assumed population. Okay, now the thing is the sample has size 16, okay, while the sample is less than 10. Test whether the population mean from which a random sample of size 16 is taken significantly less than 10. So we want to test if the population mean is less than 10. If the population from which the sample was taken is normally distributed with assumed mean this and variance that. Kind of a confusing wording, huh? Yeah, confusing wording. Okay, let's start. Let's see what's the claim first. Sometimes we just do it one at a time. Test whether, so that will be the claim. What we are testing, the population mean significantly less than 10. Okay, so let's claim, that's the claim. Claim is population mean is less than 10. I forgot the word significant. Is significantly less than 10. If the population from which the sample taken is normally distributed with assumed mean 8.4 and variance 10.8. So I think I have, I'm missing something here. I'm missing something here, but let's see the hypothesis first. The hypothesis, what we are testing is, at least we can go this far, that the mu is less than 10. Right? At least we can go that far. We know that's the claim. Okay. Now, the claim is the mean is less than 10, but the assumed mean is 8.4. So what is this 8.4 here? Once we go to test statistic, then we start seeing some issue. So we know the variance is 10.24, right? So what is the standard deviation? Population standard deviation is square root of that. I think that's 3.2. Okay, so the C, the test statistic C will be something minus 10 over 3.2 over square root of 16. Now the thing is, in this passage, we don't know what is the sample mean. Is the sample mean? That's not given in the passage. Okay, so Thomas, what is this thing actually doing? We assume the mean is 8.4, but we are not sure, right? We assume the mean of the population is 8.4, but we are not sure. So we will take this some sample. Okay, so later on we'll get sample mean. But what we really need is the population mean to be significantly less than 10. That's what we need. Okay, so this 8.4 is what we assume where it's coming from. Okay, but what we really need is the mean to be less than 10. Okay, so you see in this question 3, maybe because when I edit that to make it relevant for this part, I miss one important number, that is the sample mean. Yeah, but for sure that the claim is is what we have here. That's the claim. This is the claim. Okay. Now the thing is this 8.4, the sample, or that's what we assume the population mean from. And from the wording up there, it is the assumed population mean. That's not the sample mean. Okay, that's not the sample mean. So that's the furthest we can go. That's the furthest we can go here. Let's continue. Back to procedure. Now, step 4. Step 4. In traditional approach of hypothesis testing, step 4 is supposed to be critical value. So let's say this. So step 1 is the claim. Step 2 is the hypothesis. Step 3 is test statistic. And step 4, there are 2 styles. The first one is critical value. Critical value. The second one is a p-value. Okay, now the first one is traditional method, traditional approach. And in the past, in my old past, I used traditional approach. Okay, but recently, in the last 2-3 years, since we use calculator, I actually moved to p-value approach. Yeah, both of them will come up with the same conclusion though. Okay, now I will teach you p-value approach. I will not teach you critical value approach. Okay, now, and especially because p-value approach is the one being used a lot more recently in research. So that's why I will teach you a p-value method. Okay, now what is p-value? Now p-value of a test statistic from step 3. When we get the test statistic from step 3, the p-value of that is the probability of obtaining the value of test statistic or more extreme, assuming the null hypothesis is true. Now, we can informally say that p-value of a test statistic is the area of the tail cut from the test statistic. So you can see that picture here. Okay, so suppose we get the test statistic, right? And then we want to find the p-value. Now the p-value is the area of the tail from the test statistic in step 3. Now, the direction of the tail, is it the tail goes to the right or to the left, depends on the alternate hypothesis we have in step 2. That's why you need to write down your step 2 and step 3 and step 1 properly before you go on further. Okay, you need to do your step 1 to 3 correctly to be able to do step 4. Okay, now how do we know if it is left tail or right tail? The one above in this picture here is right tail. It's right tail. Now, when do we use right tail? Right tail if in the alternate hypothesis, the parameter is greater than constant. If the parameter is greater than constant, then it is right tail. If the parameter less than constant, it's left tail. If the parameter is not equals to constant, that's two tail. Now, the p-value is twice the area of that one tail. I don't get it, Thomas. Don't worry, we will do example to clarify what I meant here. But I'm trying to say that suppose in your step 2, suppose in your step 2, in your hypothesis, to know if it is left tail or right tail, it depends on the alternate hypothesis. Okay, now if the mu less than, let's say, less than, what's that, 100, okay, now because it's less than, it's to the left, right? The parameter less than means to the left, okay, then it will be left tail. To show that the average is less than 100, you need to come up with the sample mean that is significantly less than, not just a little bit less than. So what happened is, to show that the mu is, for example, less than 100, you need to come up with the test statistic. You need to come up with a test statistic that is significantly different from, significantly less than. Less than. It means it goes to the left, significantly less than that 100. Not just barely less than and have the big chance of distorted by sampling error. Okay, it is possible that the mean is actually less than 100, but it is also possible the mean is not less than 100, but the sample mean is just happen to be less than 100. Okay, again, if the sample mean is less than 100, does it imply that the population mean is less than 100? The answer is not true. Okay, now under what situation that it becomes true? If we can come up with a sample mean that is significantly less than 100. Okay, that's why then if it is less than, we make it left tail. Okay, we make it left tail, and this will be the p-value. This will be the p-value. The area is the p-value. Okay, now what happened with the right tail case? What happened with the right tail case? Well, suppose you have, let me use this here, the null hypothesis, the alternate hypothesis, the mu is greater than, let's say, 600, right? So you need to come up with a sample. You need to come up with a sample such that it's not barely greater than 600. The mean is not barely greater than 600, but significantly greater than 600. You only support this alternate hypothesis if the sample, the sample statistic, the test statistic you get is significantly greater than what is supposed to be under that assumption. Okay, that's why we get that right tail. Now, what happens if it's not equal to constant? So that's the case where the alternate hypothesis looks like this. Let's say not equals to, let's say, 120. Now, then to say that the population mean is not equal to 120, you need to come up with a sample that is significantly different from 120. But when we say difference, it may be greater than, it may be less than, right? Okay, maybe greater than, maybe less than. So how about the p-value, Thomas? Then you will find the area of that one tail. Let's say your test statistic is actually positive, right? Find the area of this one tail here, and then you double it. Tail area is that, while the p-value is 2 times. The p-value is twice of tail area. The p-value is twice the tail area. Now let's go on to step 5. Because it's so short, then I will just go ahead. In step 5, informal conclusion, in professional setting, this step may be omitted, but the majority will still include these steps. This step only give one of these phrases. Let me actually restructure that so that you see. It's either reject null hypothesis if p-value is less than alpha, fail to reject null hypothesis otherwise. So if the p-value is less than alpha, then we reject null hypothesis. What is alpha, Thomas? What is alpha? What is alpha? Now, alpha is the significant level. That's the risk of committing type 1 error. Oh, what is type 1 error here? That's rejecting null hypothesis when null hypothesis is true. Now, we reject null hypothesis once the probability of the assumption of parameter to be true is already less than the alpha. Alpha is always given in advance. If not, we use 5%. Maybe I write it down. Alpha is always given, in the problem. Otherwise, if not given, use alpha equals to 5%. Okay, that's the convention. You can say that's the convention. So we have only 2 phrases. Keep this in mind. Reject null hypothesis once the p-value is less than alpha. Fail to reject null hypothesis otherwise. Now, all time except null hypothesis may still be used by senior statisticians in place of fail to reject null hypothesis. Maybe I use thinner one, this one here. But this is all time. We don't use that anymore. Okay, this practice is less acceptable nowadays due to the nature of hypothesis testing. But I want to say that if you go to university, as I know UCLA, one of my former students went to transfer to UCLA and have a biostats class. She was doing her master's in public health and PH. And she was required to take another biostats class, and that's an easy breeze for her. And then she came back to me saying that, hey, you know what, Thomas, my professor still used that phrase, accept null hypothesis. And you are right, he is old. Okay, now nothing against old people. Okay, they are actually wiser. I just try to tell you that we should not be too rigid, too sensitive with that fail to reject null hypothesis phrase, simply because that's what the textbook say, okay? Because older statisticians, and they tend to be the teachers of the professors we have right now, still use that phrase, okay? If we say that they actually have the authority in statistic, then we should not reject what they accept, okay? If they say so, then it should be okay. But in my class, we will use fail to reject null hypothesis instead of accept null hypothesis. Now, we have done so much so far. Let's do one example, and then we take a break. Okay, and then after this one example, we take a break. After the break, we go back and do other examples again. Okay, now let's see. Question 1. This is basically the continuation from what we did earlier. A principal at a school claims that the average IQ of students in his school is above 100. So that's, I assume, that's the claim, right? The average IQ of students in the principal school is above 100. If you are following me, please write this down also. Principal school is above 100. Step 2, hypothesis. Null hypothesis, alternate hypothesis. We have done this earlier. Above 100, so the null hypothesis less than equals to 100. Side note, the one in red color you don't need to write, but if you write, I'm fine. The claim is with the alternate hypothesis, and from that claim we also know later on in preparation of step number 4, this will be right tail. Because to show that the mean is actually more than 100, you need to come up with a sample mean that is significantly greater than, and therefore it's on the right hand side of 100. Step 3, test statistic. We have Z equals to, the sample size is 40. Found to have average of 112. So the sample mean, so from that 40, we get the sample mean is 112.5. And the standard deviation, suppose overall IQ have standard deviation of 15. So the sigma equals to 15. Now, this is what I said earlier, that the alpha usually given. But if it is not given, assume that's 5%. Okay, that's the rule for this class. That's the rule for this class. So the test statistic will be 112.5 minus 100 over 15 over square root of 40. Then you use your calculator. I think we did earlier, huh? I think we did earlier. I get 5.27046. That's the test statistic. Step 4. How about the p-value? Now let's sketch the distribution first. That's a standard normal distribution. Okay. The test statistic is 5.27046. Now you want to find the area of the right tail. That's the p-value. That's what we need. Right? That's the p-value. So we say p-value equals to, you need to rewrite it again though. You need to rewrite this. This is the title. The p-value here is for the computation. So you should not say p-value equals what? No, 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 no. No, no, don't be that lazy. Okay, don't be that lazy. Please, please. I know there's a, Thomas, it seems to be, you're just picking on us. No, 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 no. I'm telling you what it's supposed to look like. Okay, so p-value is the area of that tail. Now notice that this is standard normal distribution, right? That's standard normal distribution. So the area in yellow there, that's the p-value, the area of the right tail. Therefore, it's given by normal CDF of 5.27046. That's the critical value the test statistic we get earlier. Okay. Comma, infinity. Go to infinity, right? E99. And this is standard normal distribution. So the mean is 0, the standard deviation is 1. Okay, but Thomas, I thought the mean is 100. No, 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 no. The mean is 100 for the IQ score. But this 5.27046 is the C score. C score, standard normal distribution, C, standard normal. So the mean and standard deviation is 1, 0, and 1 respectively. Okay, now then you use your calculator to compute this. I know that's supposed to be very small, but very, very small. Yeah, I get 6.81794 times 10 to the negative 8. Basically means the 6 is on the 8th decimal place. 6, 7, 8. Okay, let me count it again. 1, 2, 3, 4, 5, 6, 7, 8. Right? That's the 8th decimal place. Okay, which of course you can round it to 5 decimal places, but when you round it to 5 decimal places, write the zeros this way. Okay, yeah, I forgive you if you just write 0, but it's supposed to be 0 with 0, 0, 0, 0. That's how we say that I round it to 5 decimal places, and that's what I see. Okay, now the difference when you say 0, the word, the number 0 has two possible meaning. It is 0 in 0, just 0, or 0 after you round to the nearest unit. Right? Now, likewise, when you write it this way, it can be just 0, but it also means it's when you round it to 5 decimal places, it looks like that. Okay, yeah, that's the nuance of this. Now, then how about step 5, informal conclusion? Informal conclusion. Notice that the p-value is less than alpha. Yep. A p-value is less than alpha, which is 0.05. Then the informal conclusion is reject null hypothesis. Okay, it's always in step 5. In step 5, it's always only 2. Either you reject null hypothesis or fail to reject null hypothesis. Okay. We never talk about the alternate hypothesis in step 5. Never. In step 5, it's always about null hypothesis. Do you reject that or you fail to reject that? Okay. Now, that's for this time. Step 1, 2, 3, and 4, and 5. Now, if you have a chance, let me ask you to start working on question number 2. At least step 1, 2, 3. At least step 1, 2, 3. If possible, do step 4 and step 5 together with your break. We come back at 9. Let's come back at 9:15. Let's come back at 9:15. Okay, but try question 2. Try question 2. This question 2. Okay. 641 minus 600 over 100 over square root of 0.1. Get 1.83358. Step 4, let me do it here. Step 4, p value of the claim is here, and it's also right tail, huh? So pictorially, we have the situation where the test statistic is 1.83358, and we want the area to the right. Okay, so the p value is normal CDF 1.83358 P9901. Get 0.03336. Oh, then step 5. Oh, wow. 3% significance level. So this is informal conclusion. The p-value is greater than. The p-value now is greater equals to the alpha. So the conclusion will be fail to reject null hypothesis. Okay, that's for question 2. I hope that's what you get also. Question 3. Now let me. Oh, that's the earlier one. Test whether the population mean from which random sample of size 16 is taken is less than 10 if the population from which the sample was taken is normally distributed with assumed mean of, let me change the wording a little bit here. Normally distributed with variance 10.24. And then the sample mean will be, what's that? 8.4. Correct that statement a little bit. Now notice that they don't tell us the alpha, right? Alpha is 5% because not explicitly given. So if the problem does not give us the alpha, we will use 5%. Okay. Now here I change the question a little bit. So here the sample mean is 8.4. The sample size is 16. The mu, this guy here, the claim will be mu less than 10. Okay, and then this guy here is the variance, population variance is 10.24. Therefore, the population standard deviation is the square root of that. That's 3.2. Okay, let's start. I think our step 1, 2, 3 are actually the same with what we did earlier. The claim, the population mean, is less than 10. Hypothesis, null hypothesis, alternate hypothesis, mu is less than 10 because it no equal sign. Right? And while this one here is mu is greater equals to 10. We know the claim is with the alternate hypothesis again, and we know later on this will be a left tail. Less than 10, so you need to come up with a sample significantly less than 10. Test statistic. I think earlier we stopped here because we didn't know the sample mean, right? But with some rephrasing, we rephrase the situation, then we can do more. C is 8.4 minus 10 over 3.2 over square root of 16. I get negative 2 precisely. I get negative 2 precisely. So step 4, the p-value. We have left tail. The critical, the test statistic is negative 2. And we have left tail. So we need to find the area, the yellow area there, the area of the yellow region. And the p-value is normal CPF negative infinity, negative 2, 0, 1. I get 0.02275. And step 5, informal conclusion. Informal conclusion. The p-value is around 2%. The alpha, because they don't tell us, we use 5% and write it down. The p-value, again, the one in red is something you don't need to write. If you write, I'm fine, but it's actually you don't need to. Okay, then it will be reject null hypothesis. Okay, now that's up to step 5. Let's finish this up. Let's finish this up with step 6. Conclusion, the formal conclusion. In our conclusion, we will address the claim. We will address the claim. That is the one in step 1. The difference with informal conclusion, note, step 5 addresses null hypothesis in step 2. Okay, but in step 6, we address the claim. So we can see the following. The claim, from the claim, we develop the hypothesis. From hypothesis, we get the test statistic. from the test statistic we develop, we get the p-value. Now, using the p-value together with the hypothesis, we get informal conclusion. And using informal conclusion together with the claim, we get the conclusion. Okay, that's the pattern, the scheme. Now, while the wording is not that strict, some textbooks they make it very strict, and I'm not going to make it that strict. But there are some no-nos we need to avoid. There are things that you cannot do at all, and that's a sudden death. A sudden wrong. Okay. The first one, avoid using avoid using we. We act only as the administrator in using statistic. The judge will apply the informations that he or she got from the witnesses, evidence, and then from there make judgment. Okay. So, but in the end, it's the sample data that we compare the claim to. We are not saying we prove or we decide or we support the claim. No, no, no. Don't use we, don't use I. Do not put yourself in the line of fire. No, no. If you want to blame the sample. Okay. Yeah. If they want to appeal the sample. Okay. And you need to find a better data to support your claim or to refute the claim. Okay, now the sample evidence, the sample data is the evidence to support or reject the claim. We are not the one supporting or rejecting the claim. We are just administrator. Okay, it's the data that is deciding. Second, avoid the word proof because it is possible even our sample data, the evidence itself, has sampling error built into it. Okay, however much we try to avoid sampling error, that's something possibly happen and we never know. Okay, so there's a chance that the sample we use itself has sampling bias that is so big such that the sample as evidence we can avoid how to say that the evidence we get and the claim is actually not the same. Okay, now some common wording. You will see this pattern in my old tests. Okay, sometimes I use one wording, sometimes I use the other one, and again this is not strict though. Okay, the wording will be as the following. There's enough evidence or not enough evidence to support the claim that. Okay, let me show you what I'm saying. Either you use there's enough evidence or not enough evidence to support the claim that. Now it depends on, you use this word support, you use the word support if the claim goes to alternate hypothesis. Okay. If you are supporting the claim, if we are supporting the claim, then the wording will be there's enough evidence or there's sufficient evidence to support the claim. Now, if in step 5 we say fail to reject null hypothesis, then there's not enough evidence to support the claim. Now, I want you to take a look here. Take a look here. Okay. In both of these two cases, we are talking about the situation where the claim is here. Okay, the claim is here. Now, if we reject null hypothesis, rejecting null hypothesis means this is the case. If you fail to reject null hypothesis means that's the case. Okay, but remember, we in step 6 we address the claim. In step 6 we address the claim. So if your claim and your evidence are parallel, I mean they are in line, then you say that the sample data support the claim. Okay, but if the claim and the sample data are not parallel, then you say you don't support the claim. Okay, the sample data does not support the claim. Now, on the other hand, what happens if the claim actually goes to the null hypothesis? And the claim uh, reject null hypothesis. So when we say reject null hypothesis, it means we support this thing, right? That's what we go to. But that's not the claim though. That's not the claim. In step 6, you need to address the claim. Okay? So in that case, the evidence says reject null hypothesis, but the claim is null hypothesis. So we reject the claim. Okay, of course you don't say we reject the claim. No. You will say the sample data does not support the claim. The sample data reject the claim. There's enough evidence to reject the claim. There's sufficient evidence to reject the claim. Now, the last case is when the claim goes to null hypothesis and we fail to reject that null hypothesis. Then we will say there's not enough evidence to reject the claim, and so on and so forth. Now you will see, Thomas, seems like you have the play of the word support the claim and reject the claim. Now you will see in practice, you will see the following. Now, if the claim goes to the alternate hypothesis, then you try to support it. The procedure will try to support it. The procedure always try to support the alternate hypothesis. Okay, now then, if the claim goes to the null hypothesis, then the procedure will try to reject that. So depends on your claim goes to the null or alternate hypothesis, that will tell us, are you trying to support it or are we trying to reject it? But that's the more formal wording. In my class, I believe I will be good enough if you say the sample data support the claim, the sample data does not support the claim, that's good enough. Okay, but if you want to be more sophisticated, then please learn this wording. Okay, please learn further this wording. This is the theory so far. Now let's go back to how do we state the conclusion for our example question 1, 2, 3 here. Let's go back to question 1. Let's go back to question 1. We come up with reject null hypothesis, and the claim is alternate. The claim is with the alternate hypothesis, and we reject null hypothesis, so we reject this. We reject it. Okay, it means we accept alternate hypothesis, right? Okay, so we support the claim. Then step 6, we will say step 6, conclusion. Conclusion. There's enough evidence. There's enough or there's sufficient evidence and to support the claim that now Then after this word that, you need to repeat whatever you say in the claim as is. You need to repeat whatever said in the claim as is. And that is that the average IQ of students in the principal school is what? Above 100. Is above 100. That's the conclusion. Okay, remember, step 5, address null hypothesis. Step 6, address the claim. Step 5, address null hypothesis. Step 6, address the claim. Question 2. We have found that we failed to reject null hypothesis here. So how about step 6? Failed to reject null hypothesis. Then the conclusion. We tried to reject null hypothesis. We tried to reject null hypothesis, but could not. So we cannot support the claim. Right? We cannot support the claim. So conclusion, there is insufficient evidence to support the claim that girls on average score higher than 600 on SAT, the SAT for both sections. Now, I myself has a habit of inserting the alpha. So right before I start saying there is sufficient evidence, I will say at alpha equals 3%. I usually insert that, and it's not only me. I know that some people actually insert that also. So here, what is the alpha? Alpha is 5%. So we say at alpha equals to 5%. Or you can say at significance level 5%. Okay. Oh, by the way, let's explain this a little bit. Let's explain the alpha a little bit. Let's explain the alpha a little bit. Now, what happened in this question 1 is, that the p-value is so small such that assuming that the mu is 100, assuming the population mean is 100, the probability of coming up with a sample mean of 112.5 I'm sorry, the probability of obtaining a sample mean of 112.5 with sample size of 40 is 0.00000. And that probability is so small, smaller than the alpha, such that it is more likely the claim is not correct. Okay, so the sample mean comes up to be 112.5. Okay, and the sample mean is much higher than the claim. I mean, the null hypothesis, the assumed mean to be 100. Now, then, therefore, in this case, we support the claim, which is the alternate hypothesis, right? But what's the reason? The reason is we assume that even though we know that the sample may have sampling bias, okay, but compared to the claim, a sample is evidence. Compared to the claim, a sample is evidence. Okay, and we will side with the evidence. We just want to make sure that the evidence is strong enough to say something about the claim. It turns out that the claim to be above 100, right? And the sample supporting it. Okay. The probability that, maybe I write it down in green here. The probability that the X bar is greater or equals to 112.5, given the mu is 100, is so small, like it's almost impossible to happen with this condition. But this is what happened. This is the reality, right? That's the reality. Okay, this is what actually happened. If that's what actually happened there, and the probability for that to happen, knowing this is true, is so small, then we question that. And then the mu very likely is not 100. The mu very likely is greater than 100 according to the claim. Okay, that's what p-value. The probability that we come up with that sample, or even more extreme situation, given the H null constant is, in this case, is 0.00000. Okay, now then, because the probability is so small, then very likely H null is not acceptable. Okay, it's rejected. Same idea with, similar idea to this number 2. Okay, so similar idea to this number 2, we have that the p-value is 0.03336. Now, we were willing to accept the risk of only 3%. Okay, so the probability that the sample mean to be 641 or more, knowing it's supposed to be 600, is 0.03336. Now, the probability for that to happen is still greater than 3%. So we say, well, it's possible that the mean is actually 600, and you come up with the probability greater than 3%, right? And you come up with the sample mean of 641. Okay, now let me finish up this question 3 to the sample conclusion. We reject null hypothesis. So what's the conclusion? Step 6. I think I need to sneak something in here. Oh, let me erase this. Step 6, conclusion. Is it 5%? Okay, so the alpha is not mentioned. I use 5%. At 5% significance level, there is sufficient evidence to support the claim that the population mean is less than 10. Now, in this all this lesson today, in all the lesson I give you today, we only apply this to a claim about population mean with sigma known. Claim about population mean with sigma known. What happened if, so let me go on here, what if, so a big question. What if what if testing new with sigma unknown? Similar idea, very similar idea. Okay, very similar idea. Now let me pick a question from our textbook. Let's see, chapter 10, as I remember. Give me a second. As I remember, this is 10.3. Yeah, 10.3. Let me go to 10.3 and pick up some questions from there. I think I like this question. This is example 2 from 10.3. This is example 2 from 10. If you have your textbook, you may want to take a look there. This is table 1. Okay. So this is the data. Okay, and then this is the question. Okay. The font size of a Snicker bar is supposed to weigh 20 grams. Now, because of the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so the mean weight is now 20.1 grams. Now, the quality control engineer at M&M Mars, the Snickers manufacturer, is concerned about the calibration. So he obtained a random sample of 11 candy bars. So we have the sample size of 11, right? And obtain the data is there. So we will have the X bar here later on. In fact, we will also get the sample standard deviation. Okay, we'll also get the sample standard deviation. Then the alpha is 0.01. Now let's find out the X bar and sample standard deviation first. I will just use calculator. Okay, I will just use calculator. And you can go ahead using your calculator also. Okay, so what I will do is this. I go to stat and then edit. I think I will just use line list number 3. Okay, how many data to put in? 11 there. So yeah, let me just do it. 19.68. That's the first data. The second data 19.98. The third data 20.55. 21.50. 20.66. I go by the column first, but you can go either way. 20.65. 0.6. Just don't miss any data. Okay, 19.74, 19.56, 19.61, 21.02. So there are 11 data here, right? Okay, then how do I see the sample mean and sample standard deviation? I go to stats again, but this time I'll calculate the one variable stats. It will be list number 3, not list number 2. And I get that x bar equals to, let me write here, x bar equals to 20 something. What's that? 20.30091. 30091. That's for the x bar. And then the sample standard deviation 64037. 0.64037. Let me make sure I copied it right. Okay. Yeah, I try to do it fast. That's what I get. Okay, so I got this from calculator. Stat, edit to input data, and then stat, calculate one bar stats. Okay, then you will get this thing. Then using this information, we go on. Step 1, the claim. What's the claim? Should the machine be shut down and calibrated? But under what situation we shut down and calibration? If they think the mean is less than 20, right? Yeah, if the mean is less than 20. So here the claim can be many ways though. So the first possibility we say that the mean weight is less than 20. How do I know it's less than, not the mean weight is 20? Because of this. They talk about being penalized, right? The penalty for under the weight of 20. Now the thing is the mean weight is less than 20? If it is the case, then they need to shut down. Okay, so that's also another possibility. You say that the machine should be shut down and calibrated. Okay, so either this one or this one. Either one. Okay, but either way, what you are testing will be the mu, right? What you are testing will be the mu hypothesis. Hypothesis. the null hypothesis, alternate hypothesis. The null hypothesis is the mu less than 20. This is mu greater equals to 20. And the claim is here, and therefore it is a left tail. Then step 3, test statistic. Notice that we don't have the population standard deviation, right? We don't have this thing. Oops. We don't have this thing. We use sample standard deviation instead. Now, therefore, then we will use t distribution. T equals to x bar minus mu over s over square root of n. That is 20 point, what? 30091. 20.3001 minus 20 over 0.64037 over square root of 11. Then you use your calculator to compute this. And 30091 I get 1.55848. Now the thing is, we are using what? It's a left tail, right? It's a left tail. So P value, you have this T distribution with test statistic 1.55848, right? But you want left tail. You want left tail. So you know this will be more than 50%, which is strictly greater than whatever the alpha, 5%. Does it say? What's the alpha? Oh, 0.01. 0.01. Okay, so P value will be TCDF negative E99 1.55848. Don't forget, the next one after that is degree of freedom, which is 11. Okay, but we know this will be more than 50%, and we for sure will fail to reject null hypothesis. TCDF negative infinity 1.55848 degree freedom 10. Ooh, that's a big one, 0.92491. So informal conclusion. That will be fail to reject null hypothesis. And then the conclusion will be conclusion will be at 1% significant level, there is insufficient evidence to support the claim. That the mean weight is less than 20. Okay, this is where I will stop. Let me give you suggested homework. Let me give you suggested homework. Oh, by the way, you know what? Compare this result, compare my work with textbook. No, the result is actually quite different. Our textbook's way of doing things, our textbook, I think I should put apostrophe here. Example 2. So let me see that again if I did it okay. The quality control engineer is concerned about the calibration. So they calibrate that, and the mean weight is now 20.1. Okay, so our textbook way of looking at that is if it is not 20.1 mean, then they need to shut it down. The way I see is the penalty is 20. It's like if it is they advertise at 20, and if it is less than 20, they will get penalized, right? So you will see my approach is that I will focus on the penalty. The penalty, you get penalty if the mean is less than 20 while you say it's 20. Okay, but according to our textbook way of doing this problem, they're concerned with that 20.1, regardless if they get penalty or not. Okay, so this is where it gets more difficult. It's not really because of if we don't know the sigma. No, it's not. It's from the wording. The wording here is, are you concerned with the penalty, or are you concerned with that the mean is not 20.1? Okay. Okay. Now the way I see is like you already changed it to a new calibration. Do you need to recalibrate that again? Well, your concern is supposed to be, is it less than 20 grams or not? Okay. And from our information here, as long as I don't get penalized, why do you worry about that the mean is 20.1 or not? You see, that's the way I see. Okay, anyway, but please compare with our textbook. And how about the suggested homework? I would like you to do from number 3 to number 13. Yeah, 3 to 13 is good. Suggested homework, chapter 10.3, number 3 to number 11. Now, when they ask you the critical value, you can omit that for now. When they ask you the critical value, you can omit that for now. Tomorrow, what I will do, I will go on from here. I may do one problem from this 10.3 and teach you a bit about the critical value. And then I go on to, so tomorrow my plan is tomorrow I will do 9.3 and then just kind of finishing up, make it nice, and then 9.2 and then 9.4. Okay, so why do I say 9? Should be 10. So chapter 10.3 be tomorrow, and 10.2, 10.4. So tomorrow we finish chapter 10. Okay, tomorrow we finish chapter 10, and then on Wednesday we will start chapter 11. On Thursday we have tests, right? Okay, and then on Monday we will do finish up chapter 11, and then we go on to linear regression and review whenever possible. Okay, that's for today. See you then. Thank you.